This is no ordinary journey. It's the first mission of its kind, designed to capture images never seen before. Our star, the Sun, formed approximately 4.6 billion years ago. It's a G-type main sequence star, classified as G2V. Nuclear fusion within its core combines hydrogen atoms to form helium, releasing an immense amount of energy that sustains life on Earth. But the Sun's poles remain shrouded in mystery. Never before have we been able to glimpse these regions directly. The mission, managed by the Johns Hopkins Applied Physics Laboratory for NASA's Science Mission Directorate, is poised to change that. As it ventures closer to the Sun than ever before, it will capture detailed images of its north and south poles. This historic flight is a first in many ways, a pioneering mission to unveil the mysteries of our star's polar regions. With these unprecedented images, scientists hope to gain new insights into the Sun's behavior and its influence on the solar system, setting the stage for what promises to be a revelatory journey into the heart of our solar system. The Sun is not simply a bright light in our sky. It's an incredibly complex celestial body with a structure unlike any other. At its core lies the radiative zone, a region where energy is transferred outward through radiation, maintaining the Sun's nearly perfect spherical shape. Extending from this core to about 70% of the solar radius is the radiative zone, a critical part of the Sun's structure. Beyond this, there's the convective zone. This outermost layer extends from about 70% of the solar radius to its surface, or photosphere. Here, energy is transferred outward by convection currents, a turbulent, complex dance of heat and motion. Imagine this. The radiative zone is like a vast, peaceful ocean, while the convective zone is a stormy sea with hot plasma bubbling up to the surface. But why study these zones? Because understanding their intricate dynamics is crucial to unraveling the mysteries of our star. And this is where the Sun's poles come into play. They are key to unlocking these mysteries. As we journey towards these polar regions, we prepare to unveil secrets that have been hidden in the heart of our solar system for billions of years. These variations affect not only the Sun itself, but also the solar wind and magnetic field that shape the vast heliosphere, a region of space dominated by our star. The solar system, including our home planet Earth, is held in its orbit around the Sun due to its immense gravitational pull. Understanding these cycles is crucial because they influence the observations we make of our star. Imagine trying to capture a portrait of someone who keeps changing expressions. As scientists, we must account for these variations in our measurements and models. It's like trying to solve a puzzle with pieces that keep shifting, a complex challenge indeed. Yet, this dynamism is part of what makes our star so fascinating and enigmatic. As we delve deeper into the Sun's polar regions, we prepare to uncover more layers of this cosmic mystery. Breathe in the wonder and complexity of our star, a dynamic entity whose behavior changes over time. As we continue our journey, we'll unravel more secrets hidden within its fiery heart. To accomplish this, engineers design a spacecraft capable of withstanding the Sun's intense heat. The craft is built to endure temperatures over 2,000 degrees Celsius, 1193 degrees Celsius, while protecting its sensitive instruments. The spacecraft is equipped with advanced cameras and sensors to capture high-resolution images of the Sun's poles. This includes specialized lenses that can filter out the intense light from the Sun's surface. The mission involves flying over the Sun's poles at a precise distance to avoid damage from solar flares and intense radiation. This trajectory allows for safe data collection without risking the spacecraft's integrity. To ensure accurate data collection, engineers conduct rigorous tests simulating the harsh conditions of the Sun's environment. These simulations help fine-tune the spacecraft's systems and instruments. After years of preparation, the moment of launch arrives. The spacecraft lifts off from Earth, embarking on its historic mission to uncover the mysteries hidden within the Sun's polar regions. With each passing second, the spacecraft moves closer to its target. The anticipation builds as scientists await the first glimpse of the Sun's unexplored polar regions. The successful launch marks a significant step forward in our understanding of the Sun and its influence on the solar system. As we delve deeper into this journey, each new image captured promises to reveal more about our star's behavior and its impact on the cosmos. The Parker Solar Probe carries 4 suites of instruments, each playing a crucial role in studying the Sun's corona and solar wind. But one instrument stands out as particularly vital: the Whisper Wide Field Imager for Solar Probe, a camera designed to capture images of the solar wind structure. Equipped with an innovative heat shield called the Thermal Protection System, TPS, this probe is built to withstand temperatures as high as 2,500 degrees Celsius, 1,071 degrees Celsius. This unprecedented level of protection allows Parker Solar Probe to get closer to the Sun than any other spacecraft before it. Each approach brings Parker Solar Probe closer to its target, the Sun's poles. The closest approach distance is approximately 8.86 solar radii, an astonishing feat considering the intense heat and radiation. The probe was named in honor of Eugene Parker, who first proposed the concept of solar wind back in 1958. His pioneering work laid the foundation for this groundbreaking mission. As it ventures deeper into the Sun's realm, Parker Solar Probe promises to reveal secrets that will reshape our understanding of solar activity and its impact on the cosmos. With each new image captured, we take another step toward unlocking the mysteries of our star's behavior and its influence on the universe around us. And as Parker Solar Probe continues its daring mission, each discovery serves as a reminder of the extraordinary capabilities of human ingenuity and our insatiable curiosity to explore the cosmos. The mission to unravel the mysteries of the Sun's polar regions is no ordinary flight path. It involves a daring journey over both the north and south poles of our star, an area previously shrouded in mystery. This ambitious probe will brave temperatures exceeding 27 million degrees Fahrenheit to unveil secrets never seen before. Imagine a flight over the North Pole of Earth, where temperatures are about 40 degrees Fahrenheit. The Sun's north polar region is far more extreme. As the probe makes its way, it will capture data and images from regions that have never been directly observed. These areas are crucial for understanding the dynamics of our star. The south polar region is equally enigmatic. It's a zone where magnetic fields reverse polarity every 11 years, creating vast solar storms. By traversing both poles, the mission aims to uncover how these regions influence the Sun's overall behavior and the solar wind that affects Earth. This flight path is not just a technical feat, it's an audacious exploration into the heart of our star's most volatile areas. Each piece of data, each image captured, will provide insights that could redefine our understanding of the Sun and its influence on our planet. This mission represents a significant advancement in our ability to study the Sun directly and up close, offering unprecedented views into its polar regions. Whisper's camera works by taking snapshots of the solar wind and its structure, providing us with detailed visual data that will enhance our understanding of these powerful forces. This mission is not just about capturing images, it's about unraveling the mysteries of our star and its polar regions. Each photograph represents a step forward in our quest to understand the Sun's inner workings. As Parker Solar Probe ventures closer, it captures images that reveal the intricate dynamics of solar winds and the magnetic fields that shape our star's behavior. These groundbreaking images not only provide us with stunning visuals, but also pave the way for further scientific inquiry, opening new avenues of research and discovery. The significance of these polar images cannot be overstated. They offer a window into the Sun's behavior, helping us better predict solar activity and its impact on Earth. In this historic mission, we stand at the precipice of new discoveries, each image offering a piece of the puzzle that is our star, a puzzle that has captivated humanity since time immemorial. The historic mission to unravel the mysteries of the sun's polar regions has embarked on a revolutionary journey, one that promises unprecedented data on solar activity. As Parker's solar probe dives closer than any spacecraft before, it offers an opportunity to rewrite our understanding of how stars work and influence planets in our solar system. The mission aims to provide a better understanding of the dynamics at play near the sun's poles, areas that have remained largely unexplored until now. For the first time, high-resolution images capture the intricate structures and behaviors of solar winds flowing from these polar regions. These images reveal a complexity that had previously been invisible. The data is expected to help scientists predict space weather events more accurately, thereby protecting satellites and astronauts from potential hazards. As we delve deeper into the insights gained from these images, a new chapter in solar science is being written, one that could significantly advance our understanding of the sun's influence on Earth and its planets. The images from Parker's solar probe hold the promise of revolutionary insights into how solar activity shapes our cosmic neighborhood. Each image, each piece of data, is a step closer to unraveling the mysteries that have captivated humanity since time immemorial. As we continue to explore and analyze these groundbreaking images, the possibilities for new discoveries grow exponentially. However, the path to understanding our star is fraught with challenges. The extreme conditions near the sun pose significant technical hurdles for the spacecraft and its instruments. Imagine trying to operate a device in an environment where temperatures can soar up to 2,500 degrees Z, SE71 GC, 737 GCC, as experienced by Parker's solar probe's heat shield. The mission also requires precise navigation to avoid solar flares and other intense solar phenomena that could potentially disrupt the spacecraft. But despite these obstacles, scientists are eagerly awaiting the data that Parker's solar probe will gather during its upcoming flybys. Each pass promises to reveal more about the sun's dynamic nature, from the behavior of solar winds to the intricate workings of solar magnetic fields. These insights are crucial for advancing our understanding of not only the sun, but also its influence on Earth and other planets in our solar system. Beyond Parker's solar probe, future missions are already being planned to continue this exploration. As we look ahead at what's next in the ongoing quest to understand our star, one thing is clear: the journey of discovery is far from over. Each new mission brings us closer to solving the enigmas of the sun and shedding light on the mysteries that have captivated scientists for centuries. So, as Parker's solar probe continues its historic voyage until December 2025, we can look forward to the exciting revelations that await us on the horizon. And with each new piece of the puzzle falling into place, we take another step closer to truly grasping the wonders of our star. This groundbreaking endeavor, executed by Polar Electro Oy and other top scientific minds, serves as a testament to humanity's relentless pursuit of knowledge. It is through such missions that we continue to forge our legacy of discovery. The revolutionary data captured by these advanced instruments provides an unprecedented look into the sun's polar regions, revealing new insights and deepening our understanding of this critical component of our solar system. As we continue to explore the mysteries of the sun, these technological advancements pave the way for further discoveries and a deeper grasp of our star's behavior and influence on its surroundings. This dynamic environment is a result of the relentless solar wind, a stream of charged particles that continuously flows outward from the sun's corona, creating unique phenomena in the polar regions. At the poles, where the sun's magnetic field is weaker, the solar wind can interact more directly with the corona, creating intriguing phenomena that are only now coming to light. For instance, scientists have observed dramatic changes in the structure and temperature of the solar wind as it encounters the magnetic field at the poles. These interactions also generate peculiar waves and eddies within the solar wind, providing fresh insights into its behavior under varied conditions. As we delve deeper into these observations, it's clear that the polar regions of the Sun offer a unique window into the complex dynamics of our star's outer atmosphere. These discoveries are not merely academic. They have profound implications for understanding and predicting space weather events that can impact Earth and its technology-dependent society. The Parker Solar Probe's mission is a testament to human curiosity and technological prowess, as it braves the harshest conditions to unravel the mysteries of our cosmic neighborhood. With each new discovery, we inch closer to a comprehensive understanding of the Sun and its influence on the celestial bodies that orbit it. These observations underscore the importance of exploring the polar regions, where the Sun's secrets are written in the complex dance of the solar wind and magnetic field. Dive into the Sun's polar regions, where a dance of cosmic proportions unfolds. Coronal holes, dark patches on the solar surface, play a pivotal role in shaping this intricate ballet. These regions are characterized by open magnetic field lines that stretch into space, allowing solar wind to escape more freely. Observations from missions like the Parker Solar Probe reveal that these holes significantly influence the polar magnetic field and solar wind structure. These images provide new insights into how the magnetic field at the poles interacts with solar wind from coronal holes. Together, these observations add another layer to our understanding of polar dynamics, showing how coronal holes shape the intricate dance of solar wind and magnetic field. Imagine a vast, invisible ballet where every move is choreographed by the Sun's magnetic forces and influenced by these openings. This complex interplay at the poles highlights the importance of studying these features directly. Each observation brings us closer to deciphering the Sun's secrets. And as we deepen our knowledge, the mysteries of our star begin to unravel, one fascinating discovery at a time. For now, we settle on the beauty of this cosmic dance, an intricate tapestry woven by forces beyond our immediate grasp. As we marvel at the intricate cosmic dance of our star, it's worth pausing to consider how this historic mission stands among its predecessors. Comparative analysis with other solar missions reveals a tapestry richer and more nuanced than ever before. Previous missions, such as the Helios probes and Solar and Heliospheric Observatory (SOHO), have offered crucial insights into the Sun's dynamics. However, they mainly focused on equatorial regions, leaving the polar areas relatively unexplored. These measurements have shed light on the complex interactions within the solar wind, showing variations that weren't detectable from equatorial observations alone. This new data is essential for understanding how space weather affects Earth and other planets in our solar system. In conclusion, this mission represents a pivotal step forward in our quest to unravel the mysteries of our star. By filling gaps left by previous missions and challenging existing theories, the Parker Solar Probe has significantly enhanced our understanding of solar activity. Among the vast, swirling expanse of space, one force stands out: the solar magnetic field. This invisible web of energy stretches far beyond the Sun's visible surface, shaping its polar regions in unique and fascinating ways. At the poles, the solar magnetic field takes on a special behavior. It becomes stronger and more concentrated, creating powerful magnetic structures known as coronal holes. These coronal holes are areas where the Sun's atmosphere is thinner and cooler than average. They appear dark and ultraviolet light because less material is present to emit light. The magnetic field at the poles also influences the dynamics of the solar wind, which is a stream of charged particles that flows outward from the Sun. In regions with strong magnetic fields, the solar wind speeds up and becomes more turbulent. This increased activity in the solar wind can have significant impacts on Earth and other planets in our solar system. It can lead to geomagnetic storms and auroras, which are beautiful displays of light, but can also disrupt communications and power systems on Earth. Understanding these magnetic structures is crucial for interpreting images of the Sun's polar regions captured by missions like the Parker Solar Probe. These images reveal the complex and dynamic nature of our star, offering insights that were previously unattainable. The Sun is a dynamic and ever-changing star, with its poles being particularly active regions. One of the most fascinating phenomena occurring at these polar regions are known as coronal mass ejections, or CMEs. CMEs are massive explosions of plasma and magnetic fields that erupt from the Sun's corona. At the poles, these events are not only more frequent, but also pack a significant punch. Polar CMEs occur frequently, with studies showing that they can happen as often as every 10 minutes during active periods. These ejections release vast amounts of energy and can travel at speeds exceeding 3 million miles per hour. The causes of polar CMEs are rooted in the Sun's complex magnetic field. At the poles, these fields become more tangled and unstable, leading to frequent reconnection events that trigger the explosions. These powerful ejections can have profound effects on space weather, disrupting communication satellites, creating geomagnetic storms, and even causing aurora borealis displays at lower latitudes. Unlike equatorial CMEs, polar CMEs have a different orientation and structure due to the Sun's rotational axis. This difference can make them more Earth-directed and thus more impactful on our planet. Understanding polar CMEs is crucial for predicting space weather events, which can have significant implications for technologies we rely on daily, from navigation systems to power grids. This historic mission to unravel the secrets of polar CMEs not only expands our understanding of the Sun, but also equips us with vital tools to navigate and protect against the dynamic forces of space. By unveiling these mysteries, we take a significant step forward in predicting and mitigating the impact of space weather, ensuring our technologies can withstand the cosmic challenges ahead. Scientists define these bright points as areas where the Sun's magnetic field is particularly intense. They appear as spots, or regions, where magnetic activity is concentrated and visible from afar. The relevance of these bright points lies in their influence on solar activity cycles. As the magnetic field strengthens and weakens, so do these points, providing a window into the Sun's internal workings. By studying these bright points, researchers aim to decipher the intricate mechanisms that drive solar activity. The insights gained can inform predictions about space weather events, crucial for protecting technological systems on Earth and beyond. Though bright points are visible at both poles, the North Pole tends to exhibit more activity due to the hemisphere's overall magnetic field strength and complexity. These points underscore the interconnected nature of solar processes. They remind us that even in the vast expanse of space, the Sun's behavior is governed by precise physical laws and dynamics. As Parker's Solar Probe continues its mission, these bright points will no doubt reveal more secrets, helping to refine our models of solar physics and furthering our understanding of the universe's most vital star. This intricate dance of magnetic fields and solar activity serves as a testament to the power of observation and scientific inquiry, bringing us ever closer to unraveling the mysteries of our cosmic neighbor. And so, the journey continues, one bright point at a time, deepening our knowledge and appreciation for the complexities that govern our star's life cycle. The Sun's vast magnetic field is not static. It pulses and shifts in a rhythmic dance known as the solar dynamo. At the heart of this phenomenon lies the magnetic field's origin, the solar dynamo itself. Scientists believe that the dynamo operates like a giant electromagnet, driven by the Sun's rotation and the churning of its hot plasma. By studying the polar regions, where magnetic field lines converge, scientists hope to refine their models of how this complex dynamo works. Observations at the poles could reveal crucial insights into how the Sun's magnetic fields are generated and sustained over its 11-year solar cycle. These observations might even explain why the Sun's north pole has a magnetic field that is nearly twice as strong as the south pole's. Understanding this asymmetry could lead to more accurate predictions of solar activity and its impact on Earth's climate and communication systems. As the mission continues, each new data point from the poles brings us closer to unraveling one of the universe's most enduring mysteries. At the very edges of our star, where the Sun's immense heat and light begin to dissipate into the cosmic void, a peculiar phenomenon emerges: polar coronal loops. These loops are visible only in the Sun's polar regions, where magnetic fields arch and curve in intricate patterns, tracing the path of solar wind as it escapes into space. The Parker Solar Probe, with its suite of instruments including the Whisper camera, has been our eyes in this unexplored territory. Whisper takes images of these loops, revealing the complex dance between magnetic fields and solar wind that shapes the Sun's polar dynamics. Each loop stretches far into space, like a cosmic bridge connecting the Sun to its environment. In these polar regions, the magnetic fields are stronger and more chaotic than anywhere else on the Sun's surface. The loops not only guide solar wind, but also play a crucial role in how the Sun's magnetic field evolves and changes over time. By studying these loops, we hope to unravel some of the deepest mysteries about how our star works and influences its surroundings. Though we still have much to learn, each new observation brings us one step closer to understanding the intricate choreography of our stellar neighborhood. The Parker Solar Probe, by venturing where no spacecraft has gone before, is revealing the Sun's secrets one brilliant image at a time. As the Parker Solar Probe ventures into uncharted territory, it uncovers secrets that have long eluded our grasp. Among these mysteries are polar cosmic rays, highly energetic particles originating from the Sun's polar regions. The observation of these cosmic rays has significant implications for understanding solar activity and structure. Scientists believe that these polar cosmic rays are accelerated by powerful magnetic fields near the Sun's poles. The process involves a complex interplay of forces, propelling particles to incredible speeds. The exact mechanisms behind this acceleration remain an active area of research. One theory suggests that the magnetic reconnection events, where magnetic fields realign abruptly, play a crucial role in boosting particles to such high energies. These energetic particles could have profound effects on the Sun's activity and the wider solar system. Their presence may influence the behavior of solar flares and coronal mass ejections, which in turn impact Earth's magnetic field. To put it into perspective, imagine a particle with the energy equivalent of a freight train moving at high speed. Such particles can disrupt satellite communications and even endanger astronauts in space. The study of polar cosmic rays is not only advancing our knowledge of the Sun, but also enhancing our ability to predict and mitigate the effects of space weather on Earth. Through these discoveries, we are gaining a more comprehensive view of the energetic processes that shape our star and its influence on the cosmos. As Parker Solar Probe ventured closer to the Sun, one of its primary objectives was to investigate an intriguing phenomenon known as magnetic reconnection events. These occurrences are key to understanding the dynamic processes that drive solar activity and influence our star's behavior. The Sun, despite its appearance of serenity from Earth's perspective, is a churning cauldron of energy. Its magnetic field, which stretches far into the solar system, plays a crucial role in shaping this activity. One of the most fascinating aspects of the Sun's magnetism is how it can suddenly and dramatically reconfigure itself through a process called magnetic reconnection. During these events, the magnetic field lines that would normally stretch from one pole to another undergo a rapid realignment. This realignment can release enormous amounts of energy into space in just fractions of a second, a phenomenon akin to explosions happening on an astronomical scale. These observations reveal that magnetic reconnection events are far more common in the Sun's polar regions than previously thought. They play a significant role in driving the solar wind and shaping the structure of the corona, the outermost layer of the Sun's atmosphere. The data from Parker Solar Probe also showed that these reconnection events can occur in a matter of seconds, highlighting the rapid and dynamic nature of solar magnetism. This understanding is crucial for predicting space weather events, which can have significant impacts on Earth's technological infrastructure and astronaut safety. By providing such detailed observations and measurements, the Parker Solar Probe mission is shedding new light on the magnetic processes that drive polar activities. This knowledge not only enhances our understanding of the Sun, but also helps in better preparing for the consequences of solar activity here on Earth. As Parker Solar Probe drew closer to the Sun, it made a remarkable discovery: the presence of a polar jet stream. This stream is not your typical solar wind, it's a concentrated current with unique properties. This stream is a fast-moving river of charged particles and magnetic fields that snakes through the Sun's atmosphere with velocities reaching up to 1 million miles per hour. But what makes this polar jet stream so significant? Its composition is unique, carrying different ratios of elements and isotopes compared to the regular solar wind. These discoveries about the polar jet stream are more than just fascinating scientific facts. They hold the key to understanding how solar activities impact the wider solar system. The influence of this powerful stream on the overall behavior of the Sun's atmosphere could have far-reaching implications for our understanding of solar dynamics. Understanding how these polar jets influence overall solar behavior advances our knowledge of the Sun's intricate workings and helps in better preparing for the consequences of solar activity here on Earth. With each piece of data gathered, we unravel another layer of the Sun's mysteries. And as Parker Solar Probe continues its journey, it brings us ever closer to unlocking the secrets hidden within our star. For now, we settle back and let the probe continue its historic mission, carrying with it the promise of new discoveries and a deeper understanding of our place in the cosmos. But our understanding of this celestial dynamo has been somewhat lopsided, focused mainly on its equatorial regions. Now, a pioneering spacecraft is set to illuminate one of the Sun's most elusive and intriguing features, its polar regions. The Sun's poles are a mystery wrapped in an enigma. Unlike the equator, where solar activity is well studied and predictable, the polar regions harbor unique phenomena called polar flares. These flares are not your ordinary solar outbursts. They exhibit behaviors and effects that are markedly different from their equatorial counterparts. The polar regions also play a significant role in shaping space weather, those celestial storms that can wreak havoc on our technological infrastructure. These images promise to reveal not just the raw beauty of the Sun's polar regions, but also the intricate mechanics behind the polar flares. Understanding these dynamics is crucial for advancing our ability to predict and prepare for space weather events, which can have profound implications for life on Earth. With each revolution around the Sun, the mission will unveil more of these celestial secrets, drawing us ever closer to fully comprehending our star's complex dance. As we settle into this new era of solar exploration, one thing becomes increasingly clear: the Sun, in all its majestic complexity, holds secrets that will continue to amaze and inspire us. These jets are massive streams of charged particles that erupt from the Sun's polar regions, carrying with them a significant amount of energy and magnetic field. These plasma jets are believed to originate from regions where the Sun's magnetic field is particularly strong and complex, creating conditions ripe for such eruptions. As these jets travel through the solar wind, they significantly alter its structure and composition, providing new data on the dynamics of this vast region of space. Scientists are particularly interested in understanding how these jets interact with the surrounding environment and shape the overall behavior of the solar wind. These measurements provide a clearer picture of how the plasma jets influence the broader dynamics of the Sun's outer atmosphere, offering new insights into little-known aspects of solar polarity. As we continue to analyze the data from this historic mission, the mysteries of our star's polar regions are slowly being unraveled, revealing a universe of fascinating and complex phenomena. Though much remains to be discovered, each observation brings us one step closer to understanding the full scope of the Sun's dynamic nature and its profound impact on our solar system. Polar X-ray emissions are high-energy X-rays that originate from the Sun's poles. These emissions provide a unique window into the solar activity and structure, offering insights that visible light observations cannot. The significance of these emissions lies in their ability to reveal the dynamics of the Sun's magnetic field and plasma environment near its poles. This information is crucial for understanding how solar activity varies with time. This data will not only enhance our scientific knowledge, but also help predict space weather events more accurately. Space weather has a significant impact on satellite operations, astronaut safety, and even power grids on Earth. Imagine standing at the edge of a cliff, looking out over an immense, turbulent sea. That's what studying solar activity feels like: vast, complex, and full of unpredictable forces. Each X-ray pulse from the Sun's poles is like a whisper from a distant realm, carrying secrets that can unlock the mysteries of our star's behavior. With each new discovery, we not only expand our knowledge, but also appreciate the intricate beauty of the universe's grandest performances. So, let's explore these polar X-ray emissions and unravel the hidden secrets of our star. It's a journey that promises not just knowledge, but also a sense of wonder at the cosmos we inhabit. Each beat of data captured by the Parker Solar Probe is a step forward in this grand adventure, an adventure that brings us closer to understanding our own place in the cosmos. As the Parker Solar Probe continues its historic mission, it uncovers mysteries far more intricate than sunspots alone. Enter the enigma of polar dark spots, regions on the Sun's poles that remain perplexingly cool compared to their surroundings. Formed within the Sun's magnetic field lines that arch over its poles, these spots are a fraction of the temperature of the solar surface. Their formation is not fully understood, but scientists suspect they play a crucial role in regulating the Sun's magnetic field. By delving into these polar features, researchers hope to unravel the Sun's magnetic cycle and its broader impact on solar weather. The implications of these discoveries are profound, potentially leading to more accurate predictions of solar flares and coronal mass ejections. And so, this grand adventure continues, unveiling the mysteries of our Sun and bringing us ever closer to the stars. This advanced shield will protect the probe as it ventures into the heart of the Sun's polar vortex, a region where the solar wind swirls at speeds up to 600 kilometers per second. The Sun's poles are unlike any other part of our star. They are dynamic, ever-changing regions where powerful magnetic forces shape the solar wind. These vortices form due to the Sun's differential rotation. Its equatorial regions rotate faster than its polar regions. This difference in speed creates a complex set of magnetic fields that twist and turn as the Sun's surface rotates. The result is a continuous flow of charged particles, electrons, protons, and helium ions that stream outward from the Sun at tremendous speeds. This camera captures high-resolution images of the solar wind's structure and behavior, providing scientists with unprecedented data on these elusive vortices. This historic mission not only brings us closer to the Sun, but also reveals the intricate ballet of forces that shape our star and its environment. As the Parker Solar Probe dives deeper into the Sun's atmosphere, it uncovers a complex dance of forces that shape our star and its environment. At the heart of this celestial ballet are polar solar flares, massive eruptions that release a tremendous amount of energy into space. These flares are born from the tangled magnetic fields that crisscross the Sun's polar regions. As these magnetic fields twist and tangle, they can suddenly snap like a rubber band, unleashing a torrent of charged particles and radiation. When these flares collide with Earth's magnetic field, they can trigger geomagnetic storms that disrupt communication satellites and power grids. This historic mission to the Sun's polar regions, therefore, is not just about exploring the unknown, but also about unlocking the secrets that could safeguard our planet. And as the probe continues its journey, each new insight brings us one step closer to unraveling the mysteries that have long shrouded our star's polar regions. The polar corona, the outermost part of the Sun's atmosphere, is a region of immense interest for astrophysicists. By studying this area directly, we can gain insights into the behavior and properties of stars beyond our own. The polar regions of the Sun are particularly intriguing because they exhibit different dynamics compared to its equatorial zones. These differences can provide clues about how magnetic fields and solar wind interact with stellar surfaces. These observations will help scientists understand the complex interplay between the Sun's magnetic field and its corona, which is critical for unraveling the mysteries of stellar physics more broadly. By studying the polar corona, researchers aim to develop a deeper understanding of how stars like the Sun generate and control their vast magnetic fields. This mission represents a major step forward in our ability to directly observe and analyze solar phenomena that were previously beyond reach, offering unprecedented data for scientific exploration. The broader scientific value of studying the solar poles cannot be overstated. It offers a unique window into the fundamental workings of stars and could revolutionize our understanding of stellar physics. Imagine the dynamo as a colossal, invisible engine deep within the Sun, spinning with such force that it generates magnetic fields of unfathomable strength and complexity. These fields extend outward, shaping the Sun's corona and driving solar activity. Scientists believe that understanding the polar solar dynamo could unravel the mysteries of stellar evolution itself. By observing how the Sun's magnetic field is generated and maintained, we gain valuable insights into the fundamental processes that drive all stars. As the Parker Solar Probe delves deeper into the Sun's polar regions, it will provide unprecedented data that could revolutionize our understanding of stellar physics and the dynamics that govern celestial bodies. As we continue to unravel the mysteries of the Sun's polar regions, we draw closer to comprehending not just our own star, but the vast array of stellar bodies that populate the cosmos. This dynamic zone is where the Sun's magnetic influence interacts with the constant stream of charged particles that make up the solar wind. By delving into the formation and behavior of the polar magnetosphere, scientists aim to predict these space weather occurrences more accurately. Imagine a ballet performed on an interstellar scale where every movement is dictated by the invisible hand of magnetic forces. Just as our planet's spinning creates distinct weather patterns at the poles versus the equator, the Sun, too, exhibits fascinating differences between its polar and equatorial regions. At the Sun's equator, it completes one rotation approximately every 25 days. But as you journey towards the poles, this rotation slows to about 36 days. This variation in solar rotation sets up a dynamic interplay between the Sun's internal layers and its outer convective zone, particularly at the poles. Above this lies the convective zone, an outermost layer where heat is transported through the movement of gas, a process known as convection. At the equator, these convection currents are relatively stable and predictable, driven by the Sun's faster rotation. But as we move towards the poles, where the Sun's rotation is slower, these convective currents become more turbulent and erratic. This turbulence in the polar convection zone plays a significant role in solar dynamics, influencing magnetic field generation and space weather events. It's like having two different personalities within the same star, a more ordered, predictable region at the equator and a wilder, unpredictable side near the poles. Understanding these differences is crucial for predicting space weather events that can impact communication systems on Earth and satellites in orbit. So, next time you look up at our star during the day or night, remember that beneath its serene surface lies a complex dance of convective forces, each with their unique role to play in the Sun's grand ballet. But beneath the serene surface, a different kind of storm brews, polar solar flares. These powerful explosions originate from the sun's poles and have significant implications for Earth and the wider solar system. Polar solar flares are not as frequent as their equatorial counterparts, but they pack a powerful punch. They occur approximately every 40 days and can release up to 10 times more energy than the average solar flare. This intense energy erupts from the sun's poles, traveling at speeds of over 6 million kilometers per hour. These storms can knock out power grids and communication systems, leaving communities in the dark. In space, polar solar flares pose a significant threat to astronauts and satellites alike. The intense radiation from these flares can be dangerous for unprotected personnel in orbit. Fortunately, missions like the Parker Solar Probe are providing unprecedented data on these phenomena, helping us predict and mitigate their effects. Understanding polar solar flares is not just about danger, it's also about harnessing the sun's power for new technologies. By studying these powerful eruptions, we can learn how to better utilize solar energy, potentially transforming our future energy landscape. The polar chromosphere is the region of the sun's atmosphere located above the north and south poles, characterized by its distinctive temperature variations and chemical makeup. Unlike the equatorial regions, the polar chromosphere experiences significant fluctuations in temperature that are intricately tied to the sun's 11-year solar cycle. These temperature variations, ranging from around 4,000 degrees Celsius to as high as 20,000 degrees Celsius, play a crucial role in the sun's overall energy output and influence on solar activity. The dynamic nature of these temperatures contributes significantly to the formation and behavior of solar flares and coronal mass ejections near the poles. The composition of the polar chromosphere is also noteworthy. It contains a mix of various elements, including hydrogen, helium, and trace amounts of heavier elements, such as iron and calcium. These elements are heated to extreme temperatures by magnetic field interactions within the sun's interior, leading to the emission of intense ultraviolet radiation. Despite its remote location, the polar chromosphere is not merely a passive observer. Its complex interactions with magnetic fields and high-energy particles make it an active participant in shaping the sun's behavior. This region is where some of the most dramatic solar events, such as polar coronal holes and jet eruptions, originate. For now, the spacecraft continues its historic journey, capturing unprecedented images of the sun's polar regions. Each image provides a deeper insight into the intricate workings of our star and enhances our understanding of the sun's atmosphere and its polar behavior. The solar magnetic field is a vast, dynamic force that shapes the behavior of our star. Like the invisible currents of an electric storm, it influences the sun's polar regions in ways both fascinating and complex. Coronal holes are not static. They change in size and location due to the sun's magnetic field variations. As the magnetic field lines at the poles shift and realign, so do these gaps in the solar atmosphere. The influence of these magnetic variations is profound. Near the poles, coronal holes can lead to enhanced solar wind activity, which drives space weather events like coronal mass ejections, or CMEs. CMEs are massive bursts of plasma and magnetic field that can erupt from the sun's corona, often near these polar regions where magnetic fields are most active and unstable. When a CME occurs, it can spew billions of tons of material into space at speeds up to several million miles per hour. These powerful outbursts can have significant effects on the Earth and other planets within our solar system. Scientists studying the sun are continually monitoring these magnetic fields using instruments like WISPR, which captures high-resolution images of the solar wind's structure. These observations not only deepen our understanding of how magnetic fields shape solar polarity, but also provide insights into the larger mechanisms at play within our star. As we continue to explore these magnetic variations, we are gaining unprecedented data that could revolutionize our ability to predict solar activity and safeguard technology on Earth. The journey to unveil the mysteries of the Sun's polar regions is ongoing, each discovery bringing us closer to unlocking the secrets of our star and its dynamic magnetic field. The temperature differences in the polar solar wind are also striking. The polar regions can reach temperatures as high as 2 million degrees Celsius, while the equatorial regions remain relatively cooler. This extreme environment at the poles provides a stark contrast to other parts of the Sun. As we continue our mission, these unique properties give us valuable insights into how the polar regions differ from the rest of our star. Perhaps one day, we might understand why these regions are so different and what role they play in shaping our solar system. Just as Earth's magnetic field guides the auroras that dance across our skies, the Sun's magnetic field shapes intricate loops of plasma known as coronal loops. Imagine a vast web of these loops stretching out from the Sun's surface, each loop filled with plasma heated to millions of degrees Celsius. When these loops interact or collapse, they can trigger powerful solar flares and coronal mass ejections. These explosive events release immense amounts of energy into space, influencing the entire heliosphere. This mission provided a deeper understanding of how these polar features influence the Sun's magnetic field and drive solar activity. As we continue to study these enigmatic structures, we may unravel more secrets about the Sun's behavior and its impact on our solar system. The significance of these polar coronal loops in shaping the Sun's magnetic activity cannot be overstated. They are not just passive features, they actively drive the Sun's most dramatic events and sculpt its magnetic field. But delve deeper into the Sun's enigmatic behavior, and we find another intriguing phenomenon: polar dark spots. These mysterious regions appear as dim patches near the Sun's poles and have puzzled scientists for decades. Their origin remains unclear, but recent observations suggest they might be linked to powerful magnetic fields. These regions could be where intense magnetic forces disrupt the Sun's usual brightness. As these dark spots evolve, their behavior can have significant consequences. They may contribute to sudden changes in solar activity, influencing space weather events that impact satellites in Earth's atmosphere. Understanding the dynamics of these polar dark spots is crucial for predicting such events. The Parker Solar Probe's unprecedented data is shedding new light on how these regions function and interact with the Sun's magnetic field. This mission to unveil the secrets of the Sun's polar regions is revealing that even our seemingly stable star holds enigmas yet to be fully understood. Each new discovery brings us closer to unraveling the complexities of the Sun, helping us better predict and adapt to its dynamic nature. With every revelation, the Sun's mysteries deepen, inviting further exploration and a renewed sense of awe at the cosmic dance that sustains us all. The Sun's polar regions are a mystery waiting to be unlocked, but they hold the key to something vital: predicting space weather. At the poles of our star, a complex interplay of magnetic fields shapes the solar wind, the stream of charged particles that envelops the entire heliosphere. To predict solar flares and coronal mass ejections, CMEs, that can disrupt power grids on Earth, scientists need precise data from these polar regions. Additionally, the Whisper camera captures images of the solar wind structure, giving a visual perspective on these powerful fields. With each mission like Parker Solar Probe, we inch closer to understanding the dynamics of these polar magnetic fields. These findings are essential for developing accurate models that can forecast space weather events and protect our satellites and communication systems. The practical applications of studying the Sun's poles underscore their relevance to human technology and safety in a profoundly interconnected universe. Imagine a vast, fiery tendril of gas, visible as an eerie glow emerging from the Sun's polar regions. This is not your ordinary solar phenomenon. These are known as polar solar prominences. They are among the most intriguing and mysterious features of our star's dynamic nature. Solar prominences, or filaments as they are sometimes called, form in the sun's outer atmosphere when magnetic fields tangle and twist, trapping hot gas within their loops. At the poles, these magnetic fields are particularly active due to the sun's rotation and its 11-year solar cycle. The complex interplay of these forces creates conditions ripe for the formation of polar prominences. These enigmatic structures are not merely beautiful spectacles. They hold significant clues to understanding solar activity and its impact on Earth's climate and space weather. With missions like the Parker Solar Probe capturing never-before-seen images of these polar regions, scientists are gaining unprecedented insights that could revolutionize our understanding of solar physics and its consequences. Each polar prominence is a testament to the sun's ever-changing nature, a stark reminder that even our seemingly constant star is in a state of constant transformation. In exploring these phenomena, we are not just expanding the frontiers of human knowledge, but also deepening our connection to the cosmos and the forces that shape our world. Following the historic mission to unveil the mysteries of the sun's polar regions, we turn our focus to a critical aspect: polar solar irradiance. The significance of polar solar irradiance lies in its role as a key indicator for climate studies and long-term changes in solar output. By examining the irradiance from these polar regions, we can better understand the sun's variability. These measurements are vital because they help us predict how changes in solar activity might impact Earth's climate over extended periods of time. Understanding these fluctuations can inform our models of long-term solar variability. These measurements highlight the broader implications of studying the sun's poles for Earth's climate. They underscore how the delicate balance of solar irradiance can affect long-term changes in our star's output, impacting our world in profound ways. The spacecraft's heat shield, capable of withstanding temperatures up to 2,500 degrees Fahrenheit, 171 degrees Celsius, is a testament to the extreme conditions it endures to gather this critical data. In conclusion, polar solar irradiance serves as a crucial window into understanding solar variability and its far-reaching implications for Earth's climate. By advancing our knowledge in this area, we deepen our connection to the cosmos and the forces that shape our world. Polar solar flares and CMEs can have a profound effect on the magnetosphere, the region where Earth's magnetic field interacts with the solar wind. When these eruptions occur, they can compress and distort the magnetosphere, leading to geomagnetic storms. These storms can disrupt satellite operations, causing temporary loss of signal and even damage to spacecraft. Understanding the mechanisms behind polar solar eruptions is vital for developing protective measures. Moreover, the magnetic field changes can induce currents in power grids on Earth, potentially leading to blackouts and other electrical issues. By studying polar solar activity in detail, scientists hope to improve space weather forecasting, allowing us to better protect our technology and infrastructure from these powerful events. When the sun experiences a polar solar flare, it releases an immense amount of energy that can significantly impact Earth's magnetic field and environment. These powerful outbursts occur near the poles of our star, making them particularly potent and unpredictable. Geomagnetic storms can affect a wide range of technologies on Earth, including satellite operations. The intense magnetic fields can disrupt communication signals and even cause temporary blackouts in certain systems. Additionally, these storms can induce strong electrical currents in the power grid infrastructure on Earth's surface. These induced currents can overload transformers and cause widespread power outages. The effects of polar solar flares extend beyond technological disruptions. The charged particles released during these events can also penetrate Earth's atmosphere and pose risks to astronauts in space. Understanding the mechanisms behind polar solar flares is crucial for improving our ability to forecast these events. By studying the activity near the sun's poles, scientists aim to develop more accurate models that can predict when and where these flares will occur. This enhanced forecasting capability is vital for protecting our technology and infrastructure. With better predictions, we can take proactive measures to mitigate the risks posed by these powerful solar events. For instance, a well-predicted geomagnetic storm could prompt satellite operators to temporarily adjust their system's configurations, reducing the risk of disruptions. Similarly, power grid managers can take steps to redistribute loads and prepare for potential outages, minimizing the impact on consumers. The data gathered from missions like Parker Solar Probe are instrumental in advancing our understanding of these complex solar dynamics. By studying the sun's polar regions directly, scientists hope to uncover new insights that can lead to more effective mitigation strategies and ultimately safeguard our technology and infrastructure. In essence, every revelation about polar solar flares brings us one step closer to harnessing the power of the sun's poles while protecting ourselves from their fiery wrath. The polar solar wind, the fast and hot plasma streaming from the sun's poles, plays a crucial role in shaping Earth's magnetic field and environment. As this high-speed wind interacts with Earth's magnetosphere, it compresses the day side of the magnetic field, creating a bow shock that deflects the solar wind around our planet. This compression also leads to the formation of a long magnetotail on the night side, extending far beyond Earth's orbit. The unique characteristics of polar solar wind can cause significant variations in this tail, impacting how our planet experiences space weather events. These connections can also drive currents within Earth's ionosphere, creating geomagnetic storms that disrupt power grids, satellite communications, and navigation systems. Studying the polar solar wind is vital for predicting these space weather events and mitigating their impacts on our technological infrastructure and daily lives. Scientists discovered that the sun's polar regions exhibit a unique form of oscillation, different from those at the equator. These polar solar oscillations are believed to play a significant role in transporting energy from the core outwards towards the solar surface. Unlike equatorial oscillations that propagate across the entire sun's surface, PSOs are localized to the polar regions. This localization suggests that they might be influenced by specific magnetic field configurations and temperature variations unique to these areas. Scientists hypothesize that the polar oscillations might serve as a mechanism for redistributing energy more efficiently within these distinct magnetic environments. By studying PSOs, we gain valuable insights into how the sun maintains its internal balance over billions of years. Each observation and measurement brings us a step closer to comprehending the sun's complex dynamics and its impact on the wider solar system. By piecing together these oscillatory patterns, we not only enhance our knowledge of solar physics, but also improve our ability to predict space weather events that affect life here on Earth. In the vast expanse of space, where countless mysteries still remain hidden, these polar solar oscillations represent a crucial piece of the puzzle that is our star's dynamic behavior. Venturing into the polar regions of our star, scientists have uncovered a fascinating phenomenon: unique oscillations in the sun's magnetic field. These polar magnetic field oscillations are providing deeper insights into solar activity and behavior. At the poles, the magnetic field oscillates in specific patterns that differ from those observed at the equator. These oscillations are believed to be tied to the sun's internal dynamics and could play a crucial role in modulating solar activity. The discovery of these oscillations provides a window into the complex processes that govern our star's behavior. By understanding how the magnetic field behaves at the poles, scientists can enhance their models of solar variability and its implications for space weather on Earth. These findings are particularly relevant given that the sun's activity can have profound effects on Earth's climate and technological infrastructure. By gaining a deeper understanding of the polar magnetic field oscillations, scientists aim to improve predictions of solar flares and other space weather events that can impact our planet. These polar magnetic field oscillations represent a crucial piece of the puzzle that is our star's dynamic behavior, offering valuable insights into how the Sun functions as a whole. The solar wind, a stream of charged particles emanating from the Sun, is not uniform. At the poles, it carries unique characteristics that significantly affect Earth's atmosphere and magnetic field. When solar particles from the polar regions encounter Earth's magnetic field, they can compress it on one side while stretching it out on the other. This phenomenon creates a region known as the magnetotail, which extends thousands of kilometers into space. The dynamics of this stretched magnetic field can generate powerful electrical currents, leading to intense auroras seen as the northern and southern lights. These brilliant displays are more than just a spectacle. They represent a direct interaction between the Sun's polar winds and Earth's magnetic field. But the impact of polar solar wind isn't just visual, it also has practical implications for our technology-dependent world. The charged particles can disrupt satellite communications, a critical lifeline for global navigation systems and weather forecasting. Studying these polar interactions is not just about understanding our star, it's about safeguarding the infrastructure that supports modern life on Earth. Every discovery, every image captured from within this vast and complex heliosphere brings us one step closer to comprehending the full extent of our star's influence. Beyond the radiant halo of the Sun lies a mysterious realm where the solar wind originates, polar coronal holes. These are vast, dark regions at the Sun's poles where intense magnetic fields stretch out into space, creating openings in the solar atmosphere through which the solar wind can escape. The Parker Solar Probe mission has revealed that these polar coronal holes significantly influence the properties of the solar wind. The solar wind emanating from these regions is typically faster and cooler compared to winds from other areas on the Sun. This fast-moving wind can reach speeds up to 2 million kilometers per hour, carving out the vast heliosphere that envelops our solar system. Additionally, polar coronal holes contribute to the composition of the solar wind by releasing unique particles and elements into space. The composition of the solar wind from these regions varies significantly due to their strong magnetic fields, which can trap and release different elements. Understanding how polar coronal holes shape the solar wind is crucial, because this wind eventually interacts with Earth's magnetic field. This interaction can create beautiful auroras that light up the night skies at high latitudes, but also impact space weather conditions near Earth. Recent findings from the Parker Solar Probe have provided new insights into how these polar features sculpt the broader heliosphere and influence our planet's environment. By studying polar coronal holes, we gain a deeper understanding of solar dynamics from pole to pole, advancing our knowledge of the Sun's complex nature